Hello friends, I welcome you on BYJU'S Exam Prep, India's most comprehensive preparation platform for all the engineers. All the candidates who are joining me live, just quickly confirm your presence in the comment section and tell me whether my audio visual quality, everything is clear so that we can start with the session. Till you are going to report me this, let me just brief you what is the ideal duration and what is the agenda for today's session. The ideal duration for today's session is going to be approximately 1 hour or 45 minutes. So whatever comes, and we are going to discuss some of the important multiple select questions, because as far as electrical students are concerned, we have not got MSQ questions till now, but this year be ready for the MSQ questions, because GATE exam is all about surprises. It may happen that you don't get even a single question this year also, because I cannot say anything, I cannot judge anything. I can only talk about possibilities, but you have to be ready for all the situations. If the MSQs are coming, you should be mentally prepared. It may be 10, it may be 15, it may be 5. If the MSQ questions not coming, then it is regular, used to business. So everybody who is joining me live, everything is clear? Okay, Raghu. So let us start with the session. Some of you may be joining me for the first time, so there is a brief introduction about myself. My name is Ashutosh. As you can see on the screen, I have 11 plus years of teaching experience, completed MTech from BYJU in 2010, written a couple of books, and these are my areas of expertise. Before we start the session, some of the important informations I want to convey with you so that you get benefited. Everybody's favorite and one of the legendary faculty for electronics engineering, Rakesh Talreja sir, is going to conduct a mega workshop on 7 golden rules to secure a single digit rank in GATE 2024. So if you have a junior, if you have a colleague, or you yourself are interested for GATE 2024, then do not miss this workshop. It is going to be conducted on 29th of January, 12:30 p.m. in the afternoon, only on BYJU'S Exam Prep app. But to attend this workshop, you have to get yourself registered. Further, we have All India Open Mega Mock Test for GATE 2023. It is going to be conducted from 24th of January to 30th of January. So do not miss these mega mock tests. These are important to experience the real exam-like situations and how you can handle the exam pressure, and you perform better and reduce the mistakes in the real examination. So register yourself for these mega mock tests. Now we have started another important series, top 11 questions of every subject for electrical, electronics, instrumentation and computer science. Already it is started from 27th of January, that is today itself. So subscribe to BYJU'S Exam Prep so that you do not miss any of these important sessions. One of the most awaited sessions throughout the year, GATE live exam analysis, we are coming up with for all the branches on 4th, and for electrical, electronics and computer science on 4th of February and 5th of February, 1 p.m. in the afternoon and 6 p.m. in the evening. So subscribe to BYJU'S Exam Prep so that you do not miss these important sessions. Hit the like button, hit the bell icon and subscribe so that you do not miss any of the important session. Good evening, Krishna. Let us start with the first question. All these questions I have made myself. So these questions may look like simple for you, some of you, but these are important concepts which are one way or the other way going to help you in the various questions in GATE examination. Let us read the first question. It says, choose the correct options. The capacitor draws leading current from the supply. The capacitor supplies lagging current to the system. The inductor draws lagging current from the supply. The inductor supply leading current to the system. So all confusion. Let us do the basic understanding. Suppose you talk about a static inductive load. If you have a static inductive load, something like this. Now, it is nothing but a load. What is the basic nature of load? The basic nature of load is to absorb power. Yes or no? So, it is going to absorb power. Which power it is going to absorb? It is going to absorb a current which is lagging the voltage by 90 degree, which is lagging the voltage by 90 degree. So if you draw the phasor diagram, this is the reference voltage and the current drawn by the inductor is going to be lagging by 90 degree. Yes or no? The same situation you can write if you reverse the current direction. Suppose I am reversing the current direction. I am saying no, it is supplying current. Now which current it is going to supply? It is going to supply minus of IL angle minus 90. Yes or no? So just draw another diagram, phasor diagram. This is the reference voltage. Now minus of IL angle minus 90 is going to be something like this. Now you can observe it is leading this voltage by 90 degree. It means actually the current drawn by the inductor is lagging. But if I write minus of the current, it becomes leading. So can I say that your inductor basically absorb lagging reactive power, or at the same time you can say your inductor is supplying leading reactive power? Yes or no? You can do the same thing for the capacitor also. Suppose you have a static capacitive load. Static capacitive load. Something like this. Now this capacitor is again nothing but a load. So this is also going to get or take some current. Suppose the current taken by this capacitor is going to be leading if this voltage is the reference. So what is the phasor diagram? If this is the reference voltage, this is going to be the leading current drawn by the capacitor. Yes or no? Again in the same way, if you reverse the current direction, you can write minus of IC angle 90 degree. Again you draw the phasor diagram. So it becomes, I am writing here itself, if this is the reference voltage, minus of IC angle 90 degree is going to be lagging. So you can write that your capacitor is, it absorbs leading reactive power, or at the same time you can say it supplies lagging reactive power. Is it clear? Now you can very well answer this question. Capacitor draws leading current from the supply. Correct. Capacitor supplies lagging current to the system. Correct. Inductor draws lagging current from the supply. Correct. Inductor supply leading current to the system. Correct. All the four options are correct. Everybody just check it and tell me whether you are able to follow this or not. Are you getting the answer or not? Is it clear, everybody? Looks like a very simple question, but it is a good concept. You must have this much clarity. Yes, all correct. Everybody just tell me yes or no. Are you able to follow this? If you have any doubt, you can ask me. See the next question. See the next question. A single phase voltage source is mentioned. It delivers a current this. Now he is asking the source absorbs or delivers real and reactive power. So very easy question this is. Basically how you write the power. You write voltage, current, complex conjugate. What is the voltage? It is 100 angle 130 degree. What is the current? Current is 10 angle 10 degree, but you have to take the complex conjugate. So it becomes 1000, angle is 130 degree, minus, because complex conjugate, so it becomes minus 10, just add it here. So it becomes 1000 angle 120 degree. So if you solve this, I think you must be getting 500 minus J 866.67. Are you getting this? Now basically you have to follow the sign convention here. What is the sign convention for source and load? So basically it is a source. Okay. So what is the sign convention for the source? Sign convention for source. Please see very carefully. If this is a source, this is the current supplied by it and this is the voltage of this terminal, then the complex power supplied by this VI complex conjugate P plus JQ. So if P or Q comes out positive, it means this is the real power supplied, because the basic nature of source is to supply power. Okay, sorry, I have written it wrong. It is minus 500. Okay. Okay, cos and sine, na? 1000 cos 120 will be negative and 1000 sine is going to be positive. Okay. So if P or Q, any one of them or both of them comes out positive, it means this is the real or reactive power supplied. P or Q, if any one of them or both of them comes out to be negative, it means instead of supplying, it is the absorbing. It is absorbing the power. Yes or no? This is the sign convention for the source. What is the sign convention for the load? What is the sign convention for the load? See how you are writing the sign convention for the load. If this is the load, this is the voltage and this is current I, then the power absorbed by this load you are writing as VI complex conjugate, where you are getting P plus JQ, and again if P or Q comes out to be positive, what is the basic nature of load? The basic nature of load is to absorb power. So if it comes out to be positive, it means it absorbs. But if P or Q, any one of them or both of them comes out to be negative, then you can say this is the power which is supplied. I hope it is clear. So if you are getting here minus 500, it is a source. So it is going to be absorbed or supplied? It is absorbed. This is positive. Basic nature of source is to supply. So it is supplied. So the source absorbs this much real power? Correct. The source delivers this much power? Yes, correct. So A and B are going to be the correct options. Is it clear, everybody? Okay. It's not just about solving the question. When you are dealing with the MSQ question, you have to be little attentive. You have to weigh all the options carefully. And I will give you a suggestion. Okay, if you believe, then you can take it in the real examination. Better to attempt the multiple select questions in the last, whatever may be the questions. Okay, generally it is not going to be more than 15 or 20 whatsoever out of you can say around 65 questions. Not more than 20 questions are going to be MSQ. That is the maximum case. So better you keep the multiple select questions for the later part of your examination, because the starting half an hour, 1 hour, your adrenaline rush is very high. Your temptation is very high. You have lot of pressure whether I will make it or not. Okay. So in that situation, lot of pressure, it is highly possible that you may commit silly mistakes in the multiple select questions. So better once you are done with the 50-60% of the paper, then you go to the multiple select questions. Anyways, let's move on. See the next question. Choose the correct option in terms of the transmission line design. Option A says cadmium copper material we are using for high tensile strength. This is correct. Copper itself has high mechanical strength. If you compare copper with the aluminum, copper has better mechanical strength, tensile strength. But when you add cadmium along with copper, high tensile strength becomes even more better. So A is correct one. Phosphor bronze material you are using in difficult atmospheric situations, for example, marine environment, which are hazardous. So phosphor bronze, because it is least affected by the external atmosphere. So B is also correct. Option C says for same resistance, copper has more corona loss in comparison to aluminum. We are assuming because the last option says aluminum. Now please understand, if it is a copper and if it is the aluminum and you are writing the resistance of the copper is going to be rho copper L upon A copper. Resistance of the aluminum is going to be rho aluminum L A aluminum. Length we are taking as same. So for same resistance, if you equate these two resistances, so it becomes rho copper A copper, rho aluminum A aluminum. Now we all know that the resistivity of aluminum is more than the resistivity of copper, because copper is a better conductor. Yes or no? Copper is a better conductor. So you can say the cross section area of the aluminum conductor is going to be more than that of the copper conductor. So what the statement is saying, for same resistance, copper has more corona losses. Now understand, if the cross section area is more, suppose the situation is something like this. For same resistance, if this is your aluminum conductor, this is going to be your copper conductor. Now for same resistivity, for same charge density, not resistivity, charge density, okay, if you find the electric field stress at the aluminum is going to be less in comparison to electric field stress at the surface of copper conductor, and that is the reason possibility and intensity of corona in the copper conductor is going to be higher in comparison to the aluminum conductor. Is it clear, everybody? So option C is also correct. For same resistance, copper has more corona loss. Option D, skin effect is more in aluminum. This is wrong. This is wrong. Yes or no? Because you know how we are defining the skin effect. If this is your conductor and this is the region where the del now we are defining as skin depth. It is the distance from the surface of the conductor up to which effective current is present. Effective current present means beyond this current may be little bit present but not significant. So we are defining the skin effect as inversely proportional to skin depth. Because skin depth you can understand, if it is less and less, then there is more non-uniformity in terms of the current distribution. So more and more is going to be the skin effect. Now this skin depth, okay, it is inversely proportional to alpha, which is the attenuation constant. And this attenuation constant alpha is given as sigma omega mu by 2. Sigma omega mu by 2. Now 1 upon alpha means your del is inversely proportional to this, or under root 2 upon sigma omega mu. So you can write skin effect is, again you inverse it, sigma omega mu by 2. It means what? It means higher the conductivity, higher is the skin effect. Now copper is a better conductor, so definitely copper is going to have more skin effect than the aluminum conductor. So D is going to be wrong. A, B, C is the correct answer. Is it clear, everybody? Yes. See the next question. The lumped model is the aggregate effect of line parameters. This is correct, yes or no? This is correct. Lumped parameter is nothing but the aggregate effect. I hope everybody is comfortable with the lumped model. If you have any doubt regarding the lumped parameters, lumped model, you can ask me. Transient analysis follows lumped model. This is wrong. Transient analysis follows the distributed model. Steady state analysis follows distributed model. This is wrong. Basically, steady state analysis follows the lumped model and transient analysis follows the distributed model. So both these options are incorrect. D option, distributed model represents the line parameters per unit length of the line. This is correct. So just for the sake of your reference, if you have a little bit of doubt, short transmission line and medium transmission line, we have a steady state analysis. Steady state analysis means you are using lumped model. And voltage and current are parameters of the circuit, whereas when it is long transmission line, you have transient analysis. Transient analysis means it is going to be distributed model. Parameters are distributed over the length of the transmission line. And the voltage or current, they behave as traveling waves. Behaving as traveling waves. Is it clear, everybody? If anybody is not comfortable with this, you can ask me more, I can tell you more. But if you are comfortable, then okay. See the next question. A short transmission line has, it is 0.08 ohms. Sorry, I don't know what is this RM. Just remove it. .08 plus J 0.12 per unit as series impedance. Choose the correct option. So basically he is talking about the voltage regulation. So you must be aware, for the short transmission line, okay, for the short transmission line, yes, I will share. I think almost all the PDFs I have shared. If anyone is missed, you can ask me. I will share it again. For the short transmission line, the approximate voltage regulation expression is R per unit cos phi plus minus X per unit plus you are using for lagging load minus you are using for leading load. Now suppose I want to plot this, okay, voltage regulation with respect to the load power factor angle. Now understand, when phi is 0, cos 0 1, sin 0 0, so voltage regulation becomes R per unit. When phi is 90 degree, sin 91, cos 90 0, voltage regulation becomes X per unit. In between 0 and 90, when phi is equal to theta, what is theta? Impedance angle of the transmission line. Then voltage regulation is equal to voltage regulation max, maximum value of the voltage regulation, that is nothing but Z per unit, Z of the transmission line. So if you plot these points, this is phi, this is voltage regulation, and suppose when phi is 0, this is R per unit. Voltage regulation is R per unit. When phi is 90, then suppose it is X per unit. This is the point. In between 0 and 90 somewhere, when phi is equal to theta, it becomes Z per unit. So if you match all these points, you will get something like this. Now if you come to the leading side, when phi becomes negative, you know that there is one angle at which voltage regulation becomes 0, and that angle is phi is 90 minus theta. Again, when it is phi is minus 90, okay, then again it is minus x. Why you are getting minus? Because you are using the, yes, good evening Ashok. Listen. You are getting minus because you are using the voltage regulation expression for the lagging load, but still you are using it for the leading load. That is why you are getting minus. Otherwise, you will be getting plus. But please remember, it should be the maximum possible negative value of the voltage regulation. So it should be coming like this. I hope it is clear. This is minus x per unit is the maximum possible value of the negative or leading case voltage regulation. Yes or no? Now there is something very interesting you have to note down. What is that? If you see, for a lagging load, all the points, voltage regulation is always greater than R per unit. And leading load, voltage regulation is always positive for the lagging load. Suddenly you are jumping into machines right now. Everything is okay, Madhu? See, understand, when you come to a live class, okay, if you are not comfortable with the flow of the class, it is better you can ask your questions separately. I am not discouraging you. You can ask me 100 of questions separately. Join my personal Telegram channel, okay? Or the end of the discussion, we can take up questions like that. So what I was saying, yes. For the lagging load, there is always positive value of the voltage regulation, you can say. But for leading load, there is positive also, 0 also, negative also. And for leading case, voltage regulation is always less than R. So now you can easily judge it. He is saying for leading load, 8% is a possible voltage regulation value. For leading load, voltage regulation must be less than R per unit. What is R per unit? 8%. So for leading load, it has to be less than 8%. So 8% cannot be possible. So A is wrong. For lagging load, 4% is a possible voltage regulation value. You know, for lagging load, voltage regulation is greater than R per unit. Yes or no? So already it is 8%. How it is 4% possible? Not possible. So voltage regulation is greater than 8% for lagging load. This is correct. And voltage regulation is less than 8% for leading load. This is also correct. So C and D are correct, but this is wrong. A and B are wrong. Is it clear, everybody? I hope it is clear. See the next question. Choose the correct statement about a distortionless line. How you define a distortionless line? Just understand. For a distortionless line, suppose if this is the line, I am using a general case with ABCD parameters. This is supply side, this is load side. Suppose at the input, the waveform is something like this, and at the output, you have two cases. Either it is undistorted, it is not distorted, you are getting the same wave shape at the receiving end also. This is called distortionless. But suppose you are getting something like this. So this is distorted. So what do you want? You want distortionless or you want distorted line? You want distortionless line. What is the condition for distortionless line? There are two conditions. First condition, attenuation constant should be independent of frequency. Okay. Independent from frequency. It should not depend upon frequency. There should be no frequency terms in the attenuation constant. Second, phase constant should be directly or linearly proportional with omega. Linearly dependent. Is it clear, everybody? Let us check how. This is the propagation constant, which is given as alpha plus j beta, and it is given as r plus j omega L. This is g plus j omega c. Take r common from the first bracket. It becomes 1 plus j omega L upon r. And here take g as common. So it becomes 1 plus j omega c upon g. Now we are assuming, let L upon R is C upon G. We are assuming if this is correct. If this is correct, if this is true, then this bracket and this bracket is same. 1 is same, J is same, omega is same, L by R is same as C by G. So if you simplify it, it becomes under root Rg 1 plus j omega L upon R. Any one bracket you can take. Now if you compare the real and imaginary part, you will see that here alpha is under root Rg. Yes or no? And beta, that is the phase constant, is directly proportional to omega. So both the conditions fulfilled for distortionless line. So engineering services prelims examination admit card is out. So congratulations to all of you. Okay. Now these two conditions fulfilled, now you have a distortionless line. So this condition becomes the condition for a distortionless line. How to remember this? Please understand. LG is equal to RC. So most of you might be having LG company's AC in your company. In your home, yes or no? So LG AC, in place of A you write R. So you will never forget it. Just silly way of remembering it. LG is equal to RC. See the options. A distortionless line is always lossless line. Now this is very interesting. This is very interesting. A lossless line is always distortionless. A lossless line is always distortionless. But the reverse is not true. Distortionless line is not always lossless line. Yes or no? Lossless line means what? Lossless line means R0, G0. R0, G0. So when R0, G0, so this side also 0, this side also 0. It means a lossless line is always going to be a distortionless line. But even if R and G are present, you may get a distortionless line. So distortionless line may not be always the lossless line. Please understand this. So A is wrong. It's not alteration, it's attenuation constant. It's attenuation constant. Alpha is independent of frequency. This is correct. This is correct. This is the condition. Phase constant linearly proportional to omega. This is also correct. D option. A lossless line is always distortionless line. This is also correct. So B, C, D is going to be the correct answer. B, C, D is going to be the Correct answer. Yes, you're right. Okay. See the next question. A 300 kilometer long three-phase transmission line has sending end voltage characteristic impedance beta at no load. A shunt element is added so that receiving end voltage becomes equal to sending end voltage. The moment you get this statement, you should feel happy in the examination, because what does it mean? You know the sending end voltage is AVR plus BIR. Now because it is no load means IR 0. He is saying sending end voltage, receiving end voltage magnitude same. So directly you have to apply this condition. Mod A is equal to 1. Magnitude of A parameter is equal to 1. But you have to be careful because he is adding one extra element. So if this is your transmission line in general, if this is your transmission line having ABCD parameters like this, okay, now he is adding one extra shunt reactor. Yes or no? So you have to use the cascaded connection to get the equivalent ABCD parameters multiplied by this becomes 1 0 1 upon JXR, and this is 1. So I am only interested in A parameter right now. So if you see, equivalent A parameter becomes A plus B upon JXR. Now what is A and B? What is A and B? A is cos hyperbolic gamma L. Now gamma is alpha plus J beta. Now alpha is 0 because it is a lossless line. So put gamma is equal to J beta. So A becomes cos beta L. Simply. What is B? B is ZC sine hyperbolic gamma L. Again put gamma is equal to J beta. It becomes J ZC sine beta L. So now if you write A equivalent, that is cos beta L plus J ZC sine beta L upon J XR. So J will be cancelled. Now take the magnitude cos beta L plus ZC sine beta L and put it equal to 1. You know what is beta, it's given. You know what is L, it is given. You know what is ZC, just put all the values. Sorry, divided by XR also. The only thing you don't know is XR. So XR you will be getting as 1.29 kilo ohms as per my memory. Cross check it. Now why I have added the reactor? Why I have added the reactor? Because in general, no load condition, the receiving end voltage is more than the sending end voltage. That is Ferranti effect. You want to avoid that. To avoid that, it means you want to reduce the no load receiving end voltage. For that purpose, you have to connect the reactor. So he is saying the shunt element should be capacitor. This is wrong. Shunt element must be a reactor. This is correct. The shunt element can be either capacitor or reactor. This is wrong. Shunt reactor connected is 1.29 kilo ohms. That is correct. That is correct. See the next question. Choose the correct option. Series capacitor improves the voltage profile. Now you have to tell me what is the answer. I will not say anything. I want to check whether you know this or not. B option. Shunt capacitor improves the power factor of the system. Shunt capacitor rating is more than series capacitor for same voltage rise. Shunt reactor improves the power factor for leading load. Now everybody, you all have to tell me what are the correct options. One more input for the multiple select questions. For multiple select questions, you have to weigh each and every option individually. Instead of connecting them together, you just check whether A is individually correct or not. If it is correct, mark it as correct. Then check B, then check C, then check D. Is it clear, everybody? This BD you are telling about this question? Listen carefully. Let us first talk about the series capacitor. Series capacitor. This is the series capacitor JXC. This is JX line. Okay. Suppose this is the situation. Now, if this is the sending end voltage, this is the receiving end voltage, then the receiving end voltage, you are getting some improvement in the voltage, and that is given as I, that is the line current. The current in the line is I, and we are assuming the line current to be constant when you connect the series capacitor. Because if you take one bucket of water from the ocean, what will happen to the ocean? Nothing. So it's like taking one bucket of water from the ocean. It's highly inductive. Okay. So it's IXC sin phi r. This is the amount of voltage rise, improvement in the voltage. Okay. This is voltage rise because of the series capacitor. So statement 1 is 100% correct. It improves the voltage profile. There is no problem with that. Individually you have to weigh. Shunt capacitor improves the power factor of the system. Everybody must be comfortable with this. Yes, there is no problem. Option C, shunt capacitor rating is more than series capacitor for the same voltage rise. Understand. For the shunt capacitor, what is this Q shunt capacitor? What is this Q shunt capacitor? If you want to relate it, for shunt capacitor, the voltage rise is given as how? X, that is the total Thevenin reactance, Q shunt capacitor divided by V. Okay. For series capacitor, the rise in the voltage is given as I XC sin phi r. Multiply and divide by I. So it becomes I square XC upon I. This is sin phi r. What is this I square XC? This I square XC, because it is connected in series, it is nothing but the reactive power supplied by the series capacitor. So this delta V series becomes Q series capacitor upon I. This is sin phi r. This is equation number 1. This is equation number 2. For same voltage rise he is saying, so it becomes XQ shunt capacitor divided by V is equal to Q series capacitor upon I. This is sin phi r. Now Q series capacitor divided by Q shunt capacitor. Just take the ratio. So this Ix becomes here divided by V, and sin phi r comes down, so it becomes 1 upon sin phi r. Yes or no? What is this Ix upon V? What is this Ix upon V? This Ix upon V is nothing but approximately voltage regulation. Voltage regulation is very small, 2 to 5%. Whereas sin phi r is a higher value. Sin phi is always, you can say, very close to 0.8, 0.9, 0.6. So average value I am taking 0.8. So very small value divided by a larger value. So you will be getting a small value or larger value. You will be getting a smaller value. So can I write that Q series capacitor is going to be less than Q shunt capacitor? The rating of it means the reactive power supplied by the series capacitor is going to be less than the requirement of reactive power from the shunt capacitor. Can I say this? Yes or no? So option C is also correct. Option D, shunt reactor improves the power factor for leading load. Shunt reactor. Now everybody must be 100% sure that if it is a lagging load condition, yes, listen, if it is a lagging load condition, then always shunt reactor will deteriorate the power factor. Power factor is going to be reduced, yes or no? If it is a lagging load. Leading load, let us understand. Leading load is going to be something like this. Suppose this is P load minus JQ load. I have taken minus Q load because it is leading. It is leading. Now suppose you connect shunt reactor. What will happen? It is going to take some current IL angle minus 90. Okay. Just draw the phasor diagram, you will understand. Suppose this is the receiving end voltage. This is the receiving end voltage. When this shunt reactor was not connected, it was a leading load. So the current drawn by the load was leading. Suppose it is something like this. Suppose the leading current is something like this. This was IS1. Current coming from the supply going to the load when this shunt reactor was not present. In the second case, when you have connected it, now it is IS2. What is IS2? What is IS2, dear? IS2 is the current taken by the load, and it is going to be plus phi because it is leading. So I angle phi plus this current drawn by the reactor, that is IL angle minus 90. What is IL angle minus 90? What is IL angle minus 90? IL angle minus 90 is going to be something like this. Yes or no? Yes or no? This is IL angle minus 90. Now, take the summation of this. Take the summation of this. This is going to be IS2. This is going to be IS2. So initially this was phi 1 and now this is phi 2. This was phi 1 and this is phi 2. Now very easily you can understand from the diagram, it may not be that much clear, but it has to go little more. Understood? Little more. So this phi 2 you will see is going to be smaller. So phi 2 is less than phi 1. So can I say cos phi 2 is more than cos phi 1? Can I say for a leading load the power factor improves even by connecting the shunt reactor? Everybody just tell me, are you getting this or not? Is it clear, everybody? So option D is also going to be the correct option. That is why I am saying attempt the multiple select questions later on, not in the starting. Not in the starting. I hope it is clear. See the next question. An alternator, excitation EMF is given, access is given, connected to an infinite burst through a short transmission line. Impedance of this, an external element is connected in series with the line so that the real power injection is 2.5. Now please understand this. Whenever you have this type of statement in the question that some external element is connected and this is the power transfer, so first you check the condition of power transfer. For example, the condition for the maximum value of the P max is what? Is V square upon 4R at the design level. And the condition is X by R is under root 3. Yes or no? Now just cross check whether it is 2.5 or not. So if you put the values, maximum value of P max, what is V? It is 1. 1 is square. 4. What is R? R is 0.1. So it becomes 2.5. It means he is talking about this condition. X by R is equal to under root 3. But here it is XS plus the synchronous reactance X and at the same time short transmission line X, that is 0.2. So this is X line plus something external you are adding divided by R line. This should be equal to under root 3. This is 0.2, this is 0.2, it becomes 0.4 plus X line divided by 0.1, this is 1.732. So X line you are getting minus of 0.2267 per unit. Why you are getting minus sign? Minus sign tells you simply that it is capacitive. If the element is capacitive, you will be writing minus X external. So you will be getting positive value for this. Yes or no? So X external 0.2267 capacitive, B is the correct option. B is the correct option. The given condition is surge impedance loading condition. This is right or wrong? The given condition is surge impedance loading condition. This is wrong. This is not correct. It's not the surge impedance loading condition. It is the given condition is maximum power condition. Yes. This is the maximum power condition. So B and D are going to be the correct options. Is it clear, everybody? Is it clear? Okay. See the next question. Sorry. Now a generator connected to a 5-cycle circuit breaker to a transformer is rated 100 MVA, 18 kilovolt with reactances of XD double dash, XD dash and XD. It is operating at no load and rated voltage when a 3-phase short circuit occurs between the breaker and the transformer. It means at the generator terminal. What is your doubt? Sudarshan is asking if it is not satisfied. What is not satisfied? You are saying if this condition is not satisfied. If it is not satisfied, then you have to go with the conventional way of doing this, na? Yes. You know what is the equation for real power supplied. Write the equation, get the value of del, then write in terms of whatever relation is given. Okay. Then you have to go with the conventional way. The question itself is framed in that manner that you have to understand what is the twist in the question. Are you getting that? Okay. Now you see the three-phase short circuit is occurring at the terminal of the alternator. First, he is saying the sustained short circuit current. Sustained short circuit current means it is the steady state. In steady state, you have to use XD. So, what is going to be the first case fault current? It is going to be 1 upon J 1.3. This is going to be in per unit because it is steady state, sustained short circuit. Initial symmetrical RMS current is nothing but the subtransient period. For the subtransient period, initial symmetrical, it is 1 upon, for subtransient, it is XD double dash. So, it is J 0.19. Third case, IF3. The maximum, sorry, it's not IF3. He is asking the DC offset maximum value. I hope you remember this. Maximum possible DC component of the short circuit current. You remember the equation? You remember the equation? What was the equation? It was root 2 mod V mod Z sine. It was theta minus alpha e raised to the power minus r by lt plus root 2 mod V upon mod Z sine omega t plus alpha minus theta. This is the current response for a sudden short circuit at the terminal of the alternator when it is at no load. This is the DC offset. This is the DC offset because of the fault. And this is the symmetrical short circuit current. He is asking what is the maximum value of DC offset. What is the maximum value of DC offset? Maximum value of DC offset this, that is the peak. That is the peak of symmetrical RMS current, yes or not? That is the peak of symmetrical RMS current. Are you getting that? Now, what is this symmetrical short circuit current? So, let me write the base current value here. What is going to be the base current? Because everything we are getting in per unit. So, base current you have to find from this 100 MVA. This is 100 MVA root 3. What is the voltage? It is 18 kilovolt. 18 kilovolt. And no need of power factor because it is MVA only. Just find this value. What is the value you are getting for the base current? It is 3207.5. It is 3207.5 amperes. Please cross check this value as per my reference. No. Who told you this about real and imaginary part? You forget this. This is the DC offset. This is the subtransient period. This is the transient period. This is the steady state. So he's asking this value, maximum value of the DC offset. Maximum value of the DC offset. So maximum value of DC offset is going to be 2 times this initial symmetrical current. You remember that? Sorry, under root 2 times, because it is the RMS value of the symmetrical current and we have to write the peak value. So it is root 2 times this value, 1 upon J 0.19. Just solve all these 3 and multiply with this base current, because he is asking in terms of actual current value. So just solve this, multiply with the base current. You will be getting ABC all correct. You will be getting ABC all correct. Let's do the calculation part. Is it clear, everybody? You have to be very clear when you have to write the subtransient reactance, when to write the transient reactance, when to write the steady state. See the next question. This is the last question. The ABCD constant of a 3-phase transmission line are given. ABCD parameters are given. The load at the receiving end is 50 megawatt at 220 kilovolt with the power factor of this. Assume the magnitude of the sending end voltage remains constant. Now see very carefully. He is asking the magnitude of sending end voltage and the voltage regulation. In this type of situation, the only thing you have to do is you have to first write the receiving end voltage and the receiving end current. And when you are using the ABCD parameters, be careful, it should be per phase only. It should be per phase only. Listen carefully. So how you are writing the receiving end voltage? Receiving end voltage is 220 kilovolts. So it is 220 kilovolt divided by under root 3 angle 0 degree volts. What is the receiving end current? Receiving end current you can find from the load. It is 50 megawatt divided by root 3. Voltage is 220 kilovolt. And what is the power factor? 0.9. 0.9. And what is the angle? Minus of cos inverse 0.9, because it is 0.9 lagging. Current is lagging by this much power factor angle. So you got the VR and IR. Once you get VR and IR, very easily you can calculate VS. A VR plus B IR. Yes or not? Yes. But be careful. What you are getting here as VS is going to be VS phase. As per my reference, the sending end phase voltage, you will be getting 133.23. 133.23 angle you will be getting as 7.77. 7.77 degrees kilovolt. Okay. Now if you find the voltage regulation, it is going to be mod Vs upon mod A minus mod VR upon mod VR. Just put the values. You will be getting the voltage regulation as 12%. Now 99% of the people are going to mark the answer as this. So what is the sending end voltage? 99% of the students, they are going to mark C as the correct option. But be very clear here. This type of confusion may arise in the real examination. When he is giving you the line RMS voltage, then when he is mentioning nothing, he is simply saying the magnitude of the sending end voltage. He is not writing anything whether it is per phase or line. So always you go with the line voltage. Always you go with the line voltage. So this is C is not the correct option. Magnitude of that per phase voltage multiplied by root 3, that is 230.8 kilovolt, is going to be the correct answer, because you have to write line to line voltage 133.23 multiplied by under root 3, you get it 230.8 kilovolt. Everybody is getting this? and the voltage regulation you will be getting as 12%. So A and B are the correct options. So this is all from my side, friends. Thank you so much for joining me live in the discussion. I hope you got some idea about how to deal with the MSQ questions. I tried to frame these questions afresh from my side, so you must be getting some idea. Thank you so much. But before I conclude, if you have any doubt, you can ask me. Let me brief you about the GATE and Engineering Services test series. You will get unlimited access to the full-length mocks subject test. The link is given in the description. These are the important features: 60+ tests covering GATE and ESC, detailed mock analysis, virtual scientific calculator, 4,000+ practice questions, all India open mocks. It is all curated by GATE experts. So friends, this is all from my side for today. Thank you so much for joining me live in the discussion, and best wishes from my side. I hope you all are going to give your best performance in the GATE examination. Thank you so much, everybody. Thank you. Take care.